Good evening, all of you. My name is Anil Yadav, and this is the tutorial number 7 on fundamentals of micro and nano fabrication. So, I am following Professor Shankar Kumar Selvaraj's lectures for this tutorial. So, today we will see lithography. So, what is the photoresist and how can we transfer the pattern on a substrate, and all these things we will see. We will see the study about some parts of about the photoresist today, mainly about the photoresist. Okay, let us see. So first thing, what is the lithography? Lithography is nothing but it is the transfer of a pattern. Okay, transfer of pattern on any kind of substrate, wall, or it's just a transfer of pattern that can be through the end by any means. Like here, on the cylinder there is a pattern that is over there on the cylinder, and what you can do is that you can transfer on any screen. Just roll, or if there is, just dip in a ink, in any kind of ink, and roll over any kind of white paper or any sheet, that whatever the pattern on this cylinder, that will be transferred over the on the paper or cloth or anything. So like this, there are two cylinders, and there is pattern on the cylinder. Whatever we go there, if any kind of paper is going through that pattern will be transferred on that sheet. Okay, this is kind of a printing lithography. This is also a printing lithography. And let us say you must have seen any kind of scale. There is written on this, there are some letters written on that, and that we call stencil. Okay, stencil. In stencil, what happens is there are grooves. So whatever we write through the stencils, like this B, if we write like this, so on this, if we go like this, so wherever there is opening, the ink will go inside, and this letter will be printed on the paper or cloth or wherever you want to write. Okay, there is another thing. This is another kind of transferring a pattern. So this is also a kind of stencil. There is one kind of paper, and there are openings in that paper, and we just move an ink over that. Okay, so wherever there is an opening in the sheet, the ink will go inside, and that it will transfer the pattern on the wall, sometimes on the wall, sometimes on the benches. There are so many things that you can transfer the pattern over there. This is the lithography. Lithography is nothing but this is transfer of a pattern. Whatever you have the pattern that you want to get that pattern on any kind of substrate, that is the lithography. Okay, let us see. So now we will see the pattern transfer. How can we do that, and importance of the pattern transfer. So how can we do that? There are some direct methods of transferring the pattern, indirect methods, and what is a resist that is used for pattern transfer, what is mask, and some maskless lithography that is come under this direct writing kind of tool, and also in indirect writing as well. So there are some maskless technologies. Okay, and first we will see the photoresist processing. Okay, and the very important fact of why do we need the lithography is if you have a wafer. Okay, if you have some any wafer, so whatever chips that you have, there are so many devices in that, and to make the devices, you need to create some pattern. Okay, to make the devices you need to create some pattern over the substrate, and you need to make the flow of current through that certain pattern. Okay, through a certain you need to give a path to the current, so for that you need a lithography. Okay, so now let us see the photoresist processing. So how can you transfer the pattern? There are certain methods that you can use to transfer the pattern. There are direct methods, there are indirect methods. In direct methods, there is a any wafer or something. Okay, there is any wafer. So what that wafer does is, so over that wafer you can do, what you can do is, okay, what, okay, why you cannot, I cannot write, is there anything? Okay, wait. Okay. Huh. Okay, there is a wafer, and over that wafer there is something, what you can say, or that you can directly put some pattern over this, over this wafer. You can directly put the some pattern, and this is the directly writing with the ion milling, ion implanting, like laser writing. Okay, so if you have a wafer and over that there is something coated, let us say SiO2 is there. You want to make a pattern in the SiO2. You just want to etch the SiO2 from here and some places. So what you can do is, you can use the ion milling, you can use the ion implant, you can laser, you can use the laser to just etch it out. Okay, to etch it out. So this method, in just a minute, someone is, okay, yes. So you can use direct laser. Okay, that laser, what that laser will do, that laser will etch this out from directly. Whatever pattern you want to make, just you feed the pattern in through the software in that tool, and that will write whatever you want to write. Okay, and another thing is direct printing. If you have something kind of printing is like kind of stencil. Okay, if you have kind of stencil, okay, that stencil have some holes. Okay, in over that you just want to I think if you just want to deposit some metal, directly evaporate through these holes. Okay, that is direct imprinting. And molding, if you have some kind of mold, if you want to make some kind of bricks or these things, this is kind of a, you must have some mold, and that can be used for this thing. Okay, and another thing is indirect writing. Indirect writing uses some, okay, if there is a wafer, and first you create a pattern in some some layer, that we call it a photoresist. Okay, in the photoresist you create the pattern, and then remove you create that pattern, can transfer you over here, and then you can remove this photoresist. That is a sacrificial layer. Okay, sacrificial layer. Okay, this sacrificial layer is there for the indirect methods, because what you are doing, you are writing on the transferring the pattern initially on that layer, that sacrificial layer, and then that sacrificial layer will pattern can be transferred to the your substrate, and then this layer, sacrificial layer, will be removed. Okay, this is the indirect writing. Indirect writing, one pixel by pixel you will write in this one. That is kind of writing. And in indirect printing, like optical lithography, you can have a stencil kind of thing, stencil or mask. That is, there are some portions in the mask that there is a chrome coated mask that you can say. Okay, there is this mask, there are some patterns in this one. Okay, and you want to, this is transparent to UV light. There is a specific light, wavelength of light that is used, that we will come on why that specific light is, specific wavelength of light is used. And this is chrome. Okay, this is chrome, and this is transparent, and chrome coated glass on chrome CR. Okay, there is glass substrate, that is kind of substrates that you can use for device fabrications for the testing purpose. And then there is chrome over that substrate, and there is a pattern in the chrome. The UV light cannot pass through the chrome. Okay, that's why we use chrome, and there is opening in that, and that opening, which is transparent to the UV light, that will this is that the UV light will fall in this area, in this area, in this area, and in this area. The pattern is transferred through the light. Okay, on this one, this is the optical lithography. You just shine the light over the large area, and then it can be done. Okay, within seconds this pattern can be transferred. Okay, and another thing, this is electron beam lithography. In electron, okay, this is the writing kind of, and also you can use laser writing as well. Laser writing for on this on the sacrificial layer, and then that can be transferred to the substrate. And there is contact lithography and projection lithography that we will see, and whether these processes are compatible for the CMOS processing or not. This is this direct writing, this takes a lot of time, because pixel by pixel you need to write, and to write a single wafer it will take hours, maybe a single whole day or something. So that throughput for this one is very, very low. Okay, the cost of the fabrication is very high, but these processes can be used for something like for research purpose, not the industrial purpose. So this indirect method, which can be indirect methods are mainly used for the industrial purpose, because the throughput is very high in these cases, and so the cost of fabrication is less. Okay. Okay. And now lithography is kind of very sophisticated tool, and is critical. It is very highly expensive. Okay, highly expensive in the sense that it if the lamp itself costs high, because it's a UV lamp, and there are some filters, there are some if you are going for the projection lithography, there is a set of lenses in that, and they are expensive. They are not simple lenses. Okay, so fabrication cost for is high. Okay, it can make up to half of the total cost of the fabrication. Only just if your mobile is 20,000, just 10,000 can go to the lithography only lithography, not the hardware part. Only lithography can take the half of that. Okay, so I think there is something problem in, okay, no problem. And a single mask set circuit can take okay, if in your phone there are so many layers of the metal connections. Okay, there can be in a single phone chip, it can be, there can be 30-40 layers of the of metal connections, and they all need lithography. So this a single circuit can take up to 30-40 masks, and the mask itself cost high, very high. And the advanced photo mask is about 1.5 lakh USD dollars, a single mask. And just assume that you need 30 to 40 masks for a single mobile phone. Okay, so but these masks are reusable. Okay, these masks are reusable, so the total cost, the number of devices, the number of phones that you can make with a single mask, that reduces the cost of the mobile phone. Okay, and this single exposure tool cost is more than 30 million US dollars. That is what that I am talking about, the UV light lamp. Okay, that costs more than 30 million US dollars. Okay. Now, like how can we transfer the pattern on the substrate is, there is some mm, direct writing. Direct writing in the like mechanical means, take a scriber and you have a wafer, take a scriber and scribe it. That is kind of mechanical means, like AFM tip. This tip should be hard enough that can etch the substrate. Okay, so this is a AFM tip, and maybe a directed ion beam. Ion beams can etch this part away. Okay, this that can etch this part away, that can be used for the direct patterning. Okay, then another method is the indirect patterning. Transfer the pattern on the intermediate layer, then etch the substrate from this part, and by chemical means or by physical other means, so that you can do most of these things are used for dry etching. That is a part of this course, that you will learn how you can transfer the pattern on the substrate. Okay, so there are chemical etching is there is wet there is one is wet etching and one is dry etch. Okay, so through the by dry etch also you can do, by wet etching also you can do, by placing it in a chemical that can specifically react with the substrate and remove it from here. Okay, like HF can remove SiO2. Okay, by chemical means that you can do, if you want to remove SiO2 particularly from that part, that you can do, and that won't affect this that should not affect this intermediate layer. That intermediate layer material is chosen such that for the that subsequent processes can be done perfectly. And the direct writing is kind of a straightforward, like just scribing on the top. This is a physical process that you just need a scriber, or a for nano patterning you want to go, you just need to go through the AFM tip. That tip size should be small enough so that you can transfer the pattern in nanoscale regime. Okay, resolution are limited by the tip of the scriber. Okay, the tip of the scriber is limiting your resolution. That is the physical thing, that you cannot go beyond a certain limit. Okay, and non-physical scribers can yield higher resolution, like ion beam, okay, laser beam. These can give you a higher resolution. Okay, but still direct writing patterning is not preferred, because it writes pixel by pixel. Okay, pixel by pixel. So pixel by pixel it writes, it can take days to write a single wafer. To make a single phone, it can take days. So the throughput is very less, and the cost of the fabrication is very high in this case. Okay, and in indirect patterning, this is resource intense, because you need to have a very good photoresist. You need to have a very good kind of developer, uh, you should have good light source. All these things you need to have. A sophisticated tool is required, because first you need to transfer the pattern. There will be a series, whole series, that will come in subsequent slides, that you will get how difficult it is to transfer the pattern. Okay. I myself is struggling with some kind of transferring a pattern, because my mask is of 2 micron, and still sometimes I get 4 micron of the feature size instead of 2 micron. Instead of 2 micron I can get a 2.5, 3.5. So these are not desirable, but some other factors like humidity, some other environmental conditions can affect the pattern. Okay, can affect the feature size. So these things are there. So is the okay. So this is the widely accepted patterning technique, because the throughput is high. That is why, and it is reproducible, because reproducible means within the mask that you have, that can be reused so many times. And this is very well optimized technique. Okay, so reproducibility wins here, so that is why everywhere it is used. In for the industrial purpose, this is the only which is used. So in direct patterning there are various tools which can be used for the direct patterning, like ion beam milling. Milling in the sense you are just removing the material directly with the help of the ion beam. Laser writing, if you have a substrate which has glass substrates which are used, ITO coated glass substrate, there is ITO, and this is glass, and you need a pattern over that to make the solar cell for the research purpose only. If you want to check the efficiency of the solar cell, there are several people who are working on the materials and want to test their materials for the if they are good for the solar cells or not. There are, or for LEDs, for solar cells. So how can you do that? You can make a pattern on this one. First they make the pattern on this ITO. They etch the ITO here, and here only this part is left. This part is left. So how can you remove that? Just by laser. Okay, laser will ablaze this one. Ablaze in the sense that will remove directly with the high power lasers. You can remove this. And then scanning probe lithography, which is kind of a AFM tip. Okay, AFM tip, with the AFM tip kind of tip, yeah, which is a robust one, and with the maybe kind of diamond or something that can scratch. Okay, that can scratch with this one, and you can transfer the pattern. And indirect patterning is like optical lithography. That needs that needs a sacrificial layer or intermediate layer. The pattern is transferred on this one. Optical lithography, there are certain things which uses the kind of light. Okay, which uses the light, and there is writing and patterning. Okay, here there is writing, and another thing is to transfer the whole pattern, right? Indirect patterning, I think there was one thing printing. Okay, you can just directly print with the optical, not directly, indirectly printing over a large area. You can do this with the optical lithography over a large area, and throughput is high in this one. That's fine. And electron beam lithography, which uses the indirect patterning directly over that. You first, this is also a pixel by pixel, this electron beam lithography, because you uses an electron beam to write over that, over this sacrificial layer, over that intermediate layer, and that you develop it, and that pattern is transferred over the substrate. Nano imprint lithography uses, there is a kind of not a stencil, you can say the stencil also, or there is a mask, and what on the mask what is there, this is a the mask, and over here there are grooves. Okay, this is a hard mask, and this pattern, if we tightly there is a like a substrate, and over that there is a intermediate layer. If we push this with some pressure, what will happen is this pattern, wherever there is a groove, that will transferred over this. Okay, so that with the etching, so we can transfer the pattern over this just by pressing on directly. So this is also over a large area you can transfer the pattern within seconds. Okay. In indirect processing that I told you, there is a intermediate layer that is required. Okay, so first what you do is that intermediate layer is a photoresist. Okay, this is a photoresist. So on the intermediate layer, so this is the substrate. First, what you do is you coat that intermediate layer or this photoresist on the substrate. This is the intermediate layer that you can do the do spin coating process, which takes hardly a minute to make a layer over that. Okay, and then you bake this substrate to remove the solvents. Okay, to remove the solvents, you just bake this, and then this is the mask, that is the photo mask or stencil is there. So that can be a hard that can be a kind of a metallic mask, or that this can be a chrome coated glass mask. So where this is the opening, which is there is a light source. Okay, there is a light source, light is coming, which will pass through this one. Okay, that will make some changes, chemical changes in this intermediate layer. Then this intermediate layer we can remove from this part. Okay, particularly this part with some chemical means, and then we can do the dry etching. Okay, dry etching or the chemical etch. With the chemical means, we can by the means of the chemicals we can etch this part of the substrate, and this is how the pattern is transferred over the substrate. Okay, this. Okay. Now, indirect patterning is nothing but that uses, okay, this is the indirect patterning only. Then which are the tools that uses for the indirect patterning. In indirect patterning, as I told you, there is a intermediate layer. With this intermediate layer is photoresist, PR. Optical lithography, that you can use optical, there is a lamp that is this light is passed through a mask. Okay, in e-beam lithography, the beam of electrons, actually electron beam lithography, in a beam of electrons directly right on this photoresist, and then this is removed particularly from the area where the electron beam is falling. Ion beam is also does the same. Instead of electrons, you can use the ions. Okay, and this and then comes the imprint lithography. That, as I told you, there is some this stencil kind of, not the stencil, there is some mold type of thing is there. When we press against the photoresist, this will make a whole kind of thing here and here. So these things, so then the particularly when we etch it, the rate of etching not is the same, but this part will get etched faster, and this will get slower because of the height difference. Okay, so there will through that you can do the you can transfer the pattern. Okay, there are some advanced non-optical lithography, non-optical tools that we will see. Okay, So why? So there are some things. So in optical lithography base. So this is a image of the clean room. So this is very high from a very large clean room which is maintained at a very clean room is maintained at very low uh, particular particulate contaminations. Okay, there are very less number of particles, number of dust particles inside the clean room, so that they should not affect the lithography process. And another thing is these rooms are mainly with the yellow light. Okay, so this is done because this photoresist that we were talking about, this photoresist is sensitive to the wavelength of the light. Okay, if there is a the light is with the particular the wavelength is there, the wavelength in the ambient is there, so which affects the photoresist, then there won't be any use of that, because we cannot take it out. Okay, so that is there, so that is why these lithography bays are always in yellow in color because of the sensitivity of the photoresist. Okay, let us see optical lithography. Optical lithography is that uses the which uses the optical or we can say light to transfer the pattern, okay, on the substrate. Let me check out, there was a call. Just a minute. Okay, and another thing is this optical lithography. Let us see how this pattern is transferred through the optical lithography by means of the optical lithography. Okay, let us see. Okay, there is no fun. Okay, there are in okay, there are two kind of things. One is the projection lithography, one is the contact lithography. In projection lithography, the this the object is very far. Okay, object is very far from the lens. Okay, this is known as the far field imaging, and this is here is the imager, and here the far this is very far. Okay, and another thing is the near field imaging. Near field imaging or the contact lithography is okay, and in this case this object is made the shadow or something, the object is made, the image of the object is made to fall on the imager by means of the of the series of the lenses and of these things. Okay, by the optical means this is made to fall on the imager, and this is the projection lithography. And in the contact lithography, what do you there is the distance between this shadow and there is the imager is very less. Okay, that in subsequent lectures that you will understand what how does this happens. Okay, so okay, this is the kind of the projection litho, and okay, we will see in this one. Okay, there is three things are there. Okay, one is the light source, one is the illumination optics, and one is, and another thing, there is a mask. Okay, so uh, this is a kind of diverging, and this light source is kind of spreading all the sides. Okay, so light is coming from okay, wait, light is coming from here, here in these things directions. Okay, this is not kind of uh, directly in parallel. Okay, so this what this illumination optics does is, this illumination optics make sure to fall a straight, this light should fall on the mask in a straight way. Okay, this straightly will fall on the mask. Okay, so in this one there can be a contact, this wafer can be in contact with the mask, or there can be a gap. Okay, this contact, if the mask is in contact with the wafer, then it is a contact lithography. If this wafer is in not in the contact, if there is some gap in between this mask and the wafer, then this is the proximity lithography. And the another is the this is the projection lithography. The illumination optics is kind of the same that of the in this case, which is in the near field diffraction, near field imaging. And in this one, what is being done is, what can we do is, after the mask, this pattern is made to fall exactly. This pattern is transferred through this projection with a series of lenses by optical means on the wafer, kind of perfectly, so that you can go a little bit lower, not a little bit, you can go a lower feature sizes. Okay, so this projection lithography is used for the a lower feature size. Okay, this is a very complicated kind of tool, so very complicated optics is used for to make this kind of setup. Okay, this is a projection lithography. Now let's talk about the photoresist. Okay, we will see about this projection lithography, about the physics of all these illumination optics and the projection optics a bit later after this thing. So in photoresist, these photoresists are okay. There why do we use the photoresist first? Okay, what are the properties these photoresists have? Okay, this is the mask we make. The light is falling from the above through the mask. So this there is an opening in the mask which for which there is a certain pattern on the mask which we want to transfer on the substrate. Okay, so this opening, the light will go through this opening and will do the chemical changes in the photoresist. Okay, so this material absorbs the exposure light of the particular wavelength. Okay, of the particular wavelength, and there is a chemical change happens in the photoresist. Either the dissolution of this in a particular kind of solution, that will increase or that will decrease. Okay, solubility of the photoresist changes with the exposed light. Okay, so for the positive tone resist, we will see in the subsequent slides that for the positive tone resist, this the exposed part, okay, this exposed part of the photoresist will get removed in the developer. Okay, this is the lithography flow of the process flow. So initially you need to clean the wafer. There should not be any dust particles on the wafer, otherwise they will hamper the hamper the lithography, because if there is any dust particles, so that cannot be removed during so that will block the light. Okay, that will block the light on the substrate to fall for and the developer. Okay, so this photoresist will not get developed in that region. So then and then we do the dehydration bake. So if there are some uh, adsorption of water molecules on that will hamper the coating of the sub of this what to say of photoresist over that. Okay, there may be pinholes, there may be some very bad kind of adhesion with the substrate, so we need a dehydration bake for that. Okay, you need to remove the water content from the wafer and then cool down, because you generally do this dehydration bake at higher temperatures, that is around 110-120 degrees. So after the dehydration bake you need to give some time like 2 to 3 minutes to coat the another layer, to coat the layer. So the primer or adhesion promoter, like primer adhesion promoter can be HMDS or Surpass. There are some chemicals which modifies the surface of the substrate so that adhesion of the resist can be good. Okay, if the adhesion is poor, then while developing the feature size will go out. Okay, and then we coat the resist. So and after coating the resist, there is when we do the spin coating, so there is a layer that we have deposit, and after that there are some edge beads, so you need to remove the edge beads. There is a edge bead removal step. And then soft bake is after the coating of the resist, there is solvent in the resist, that's why you have done the coating. Okay, let me check if someone is there. Okay, so now after this edge bit removal, so you need to do the this soft baking. Okay, to remove the solvents from your layer, so that you can do the next step. So this solvent removal is necessary, otherwise there will be a problem in during the exposure step. Okay, so then this step just generally takes 1 minute. 1 minute of annealing is pre-exposure is fine at around in between around 100 degrees. Okay, so then you need to do the cool down step, and then you need to expose this one through the mask, so that you can transfer the pattern over the sacrificial layer or over the photoresist. Okay, so through the mask you do the exposure, and then again you do the cool down, because there are some chemical reactions happen due to the absorption of the light. There is the temperature goes up of this photoresist. Okay, so then you need to do the cool down step, that can take just 1 to 2 minutes are sufficient. Okay, then you do the post exposure bake. So to increase the kinetics of the reaction, you can do this step to the post exposure bake, so that you can your feature size can this step is also this photoresist dependent, what type of photoresists you are using. So that depends on the photoresist you need, if this post exposure bake step is required or not. Okay, and then again you need to cool down. This also takes 1 minute, hardly takes the 1 minute, and this cool down 1 to 2 minute. So this whole process doesn't take that much time, but there are so many steps in this one. And then you need to do the development. Development is done in a if you in a with a solution. Okay, that can be that we will come on the developers later on. So just need to remember there is a solution. Then you need to after this post exposure bake, you need to dip in this one. That takes around that is time dependent. So if you do that for larger time, then your feature size will be larger. Okay, so that also depends on the what type of photoresists that you are using. Okay, just a minute. And and after that you need to in after the development step that takes around 30 seconds. Okay, this development step takes around from 30 seconds to 1 minute. Okay, for some resists it take around 15 seconds as well, and that also depends on the exposure step, how with what energy you are exposing, and for how much time you are exposing. Okay, so and then you can rinse in the DI water to remove the developer, because there is developer on the substrate, and that will keep developing that, keep removing the photoresist, and your substrate, your feature size will go bad otherwise, if you want do the rinsing in the DI water. Okay, so for that also you need to take care, because these steps are critical for the feature sizes. And then comes the dehydration bake. After after DI rinsing, you need to go for the dehydration bake, and you can check in the microscope whether you are before this dehydration bake. Before this dehydration bake, you after DI rinsing, in between this one, at this point you can check in the microscope whether your feature size is perfect or not. If your feature size is not perfect, if it is underdeveloped, you can develop it more by keeping it in developer for some more seconds. Otherwise, if you have overdeveloped, you just remove the photoresist, do the process again. Otherwise you will be wasting your wafer. Okay, so at this point you should see in the microscope. Otherwise, if you are directly after this you are going for metallization, or the post processes are sometimes the metal deposition, so you will be wasting the everything later on that. Okay, and what are what are the properties of the light source that can be, what type of light source do you need to use? Okay, there is a mercury lamp. Okay, the mercury lamp is used mainly in these kind of lithography tools. So this these are the intensities of the mercury lamp on the specific frequencies. Okay, specific wavelengths. Okay, for like there is a 365, 254. This 254 goes under the deep UV light, and this is the UV light. 365 nanometer is mainly used for most of the processes. Okay, for most of the processes, like in sense also, in sense department also, this is 365 is used. Okay, and 254 is also used for smaller feature sizes. Okay, so because as you can see, when you when you pass you give the power to this mercury lamp, these many kind of the whole spectrum this it will give, but this is of no use for us, because if this give these multiple spectral lines, that will because of chromatic aberration so of the lenses, so this will damage, this will give us a imperfect kind of the pattern transfer. Okay, because of there are this is kind of a white light, because all the wavelengths are available in this one. We cannot do the photolithography with the white light, and also this photoresist is wavelength dependent. The photoresist that chemical changes are in the wavelength dependent, so we do not require these these wavelengths. So what we can do, we can filter out this wavelength only. Okay, that is according to the according to this tool we take the these photoresists with which light it is sensitive to. Okay, and for deep UV you can go a little bit lesser feature size. For the 0.35 micron technology, you can use this deep UV of this 248 nanometer of the wavelength of the light. Okay, so deep UV are kind of the this krypton of this kind of halogen source they use, halides. they use. This excited dimer, so these are the excimer, excited dimer, these are the excimer lasers. They can go with the high power and for the lower wavelengths these excimer wavelength lasers are used. Okay, for this is kind of this is a laser, not a light source. Deep UV light source are these. So light source in the laser is a very there is a beam spot only for the laser, but deep UV light source have these are can be made to parallel to fall on a substrate through the mask. Okay, through the mask on a substrate. But laser, there is a very only a small spot. With the lasers you can write pixel by pixel. Okay, pixel by pixel. But with the light source you can write within seconds. You can do the projection lithography can be done with these light sources only, not with the excimer lasers. But for the lower feature sizes you can use the lasers for maybe for the research purpose, but not for the industrial purpose. Okay, wait. Okay, now let's go on the light source, how this is made to fall parallel on a substrate. Okay, so this is the light source, this is the mercury lamp here. So these lenses are these mirrors are used to collect the light, because it is going in every direction. So to collect the light on this mirror here. So and after that this is a collimator makes it parallel. Okay, makes it parallel, and then there with a set of lenses and mirrors you can collect this light parallel and collect it light and make it fall parallel on the substrate. This is the used for in most of the lithography tools. Okay. And then now let's come on the photoresist. What are the properties of the photoresist? What is what it consists of? Okay, so in a photoresist consists of a base material which is resin, kind of a polymer which is there. Okay, and another thing is sensitizer, which is a photoactive compound which absorbs the light. Okay, that is specific to the wavelength. And there is a solvent which can there is a solvent which is these materials are soluble in that, and we can coat that with by means of the solution processing. That can be a a spray coating or or a spin coating kind of processes can be used to coat the photoresist. Okay. And then the absorption of the light, which is absorption is specific to the wavelength of the light. This material absorbs, and with specific light there is a reaction happens. So according to the Beer-Lambert's law, it absorbs the light, and okay, this is the thickness of the material. There is a light passing which is a I naught of the thickness at this position, and with the material with the absorption coefficient alpha, here will be the this I is equal to I naught e raised to power minus alpha alpha d. This is the thickness, or x, alpha x. Okay, at this position this is the x distance. So at this position there will be the intensity of the light that you can see at this point. This will be reduced. Okay, and this much of the light is absorbed in this material. So with the absorption you can that will increase the, that will do the chemical reaction. Okay, So in a refractive index medium, this has some refractive index. This photoresist will have some refractive index, which is a complex number. N is equal to n plus ik. This is the refractive optical refractive index. This is the k. Okay, this k is this alpha, this absorption coefficient depends on this the imaginary part of this refractive index, and which is equal to alpha is equal to 4 pi k by lambda. Okay, and according to the Beer-Lambert's law, if there are certain materials available, certain concentration of the solutes are available in the solvent, or if there are some, like if you have there are some things, if you have base material or sensitizer and some solvent is available in that thin film. So according to the Beer-Lambert's law, this alpha t, the total absorption coefficient, is equal to alpha 1 C1, the concentration of the material in that thin film, plus alpha 2 C2, alpha 3 CT, and this kind of. Okay. So and the another thing is, there is resin is available in that thin film. Sensitizer is there, and this solvent is there, and the reaction with the falling of the photons, there is a reaction is happening, and the product is also available in that. Okay, there is material that a sensitizer is there, and with the reaction of the with UV light, it is giving us the product P. So according to the Beer-Lambert's law, the total absorption is alpha T is equal to alpha mm. So according to this is the total absorption of the light in that thin film. Okay, the reaction product is the product is there on the expense of the material M. Okay, so if M is converted to P, this much of M is converted to P, initial concentration was M naught, so P is equal to M naught minus M. Okay, and there is an absorption of various during exposure. So there is a bleaching is there and non-bleaching is there. So alpha is equal to AM minus B, this bleaching minus the non-bleaching. Okay, and this is the thing that now the absorption kinetics. So how what are the things happening with the absorption of the light inside in that thin film? So there are three processes are happening in that thin film. One is the when there is photon is absorbed in the thin film. This is the thin film. Then the photon is absorbed. Okay, so it is heating up. Okay, there is a heat is there. This is heating up because of the lattice vibrations with the lattice vibration, and so there is a heat dissipation. And another is if there is this electron is going to conduction band, from when it is falling back, it is emitting the photon again. That is the re-emission of photon is there. That is the fluorescence. And one more thing is happening, a photocatalytical reaction is happening that we are interested in. Okay, photocatalysis, because of the particular wavelength of the light, there is a reaction happening in the sensitizer. Okay, there is a sensitizer in that thin film, so which enables the reaction. Okay, there is a reaction with the falling of the photons. Okay, so that is the thing that is the we are interested in, because there can be happening a cross linking also, and there can be there can be a breaking of bond also. If there is a breaking of bond is happening because of that light, so then it is the dissolution of that photoresist is improving. Okay, that is more soluble than the other rest of the part of the thin film where the light is not falling. Okay, if there is a cross linking is happening, if let us say this is the part, so in this part only the light is falling. Okay, so if there is cross linking is happening, then this part will get hardened. because of the cross linking of the in between the chains. So when we develop it, this part will be left behind and this part will get removed. Okay, if there is breaking of bond is happening, so then this part will get removed and that other part will get will left behind after the development. Okay, this is the thing. And now let's come on the on photoresist. This how what is happening inside the photoresist when the light falls. Okay, this is a novel like resin. So this is a resin. So inside there is a insoluble sensitizer. Okay, this is a sensitizer which is insoluble in the in a developer solution, but as the light falls in this one, so this converts in this one. Okay, there is a catalysis. This is the catalysis. So there is light is happening, photocatalysis we can say. Photocatalytical reaction is happening when the light falls on this resin, and this resin is converted into this soluble product which is an acid. Okay, this so and which is soluble in developer solution. Okay, so when wherever there is a falling of the light of the specific wavelength, so that will remove the that will break the bonds. Okay, they kind of break the bonds or make it more soluble, kind of that thing happens. And when we dip it in the developer, so this part will get removed. Okay, this part, and finally we will get this thing. Okay, now let's go. The chemistry. What we are kind of much interested in the chemistry. So what is actually happening when the light is falling on the, and what kind of products we are getting, so that it should not affect the post processing of the sample. Okay, post processing in the sense what if we can use a one more layer of the resist or not for to pattern later on, or with the higher temperatures it can sustain or not, and there are so many things. Okay, so was the insoluble. So what happens is it when we expose the light of the specific wavelength on this material, on this sensitizer, so this removes the nitrogen from here. Then there is, because of the instability of there, because of the lone pairs are there, so what will happen is there will be a rearrangement because of the instability of this intermediate. Okay, so there is a rearrangement, and when there is a we expose it to the outer environment because of the humidity. Okay, we are doing it in the environment inside a clean room. The environment is like controlled. Okay, there is a controlled environment. It's kept around 46 or 45% of the humidity, and to control that environment it takes a lot. It is very high energy intensive. Okay, so when it comes into the outer environment, so because of the H2, it will be converted into a soluble product. Okay. So now tones of the resistor, what is if there is a positive tone and if there is a negative tone, that depends on the if light is falling on that material of the part, if that is soluble or that is insoluble. Accordingly, this is the positive tone and negative tone. So if when okay, this is the substrate and this is the photoresist. Okay, this is the if after the light is after the light is falling through the mask and the exposed area is dissolving in in that photo in the developer. So then what happens, this if the exposed area is so this is a positive PR. Okay, positive photoresist. If the exposed area is cross-linking is happening, then this exposed area won't dissolve in that developer. So this is the negative PR. Okay, this is negative tone photoresist. And now the chemical amplification of process. In chemical amplification, what happens is, if you have a photon, okay, and there is a molecular chain of any photoresist, and there is a breaking of bond is happening in this chain, because of a single photon is doing photon is breaking one chain. Okay, so it will take a lot of photons to make to do the job for the, because one photon requires one is required to break the chain, a single chain, that will require a lot of photons or a lot of energy. Okay, so so to make it amplification, like one photon can do break hundred or thousands of the chains. Okay, so it will require less energy, so that can be done with the chemical amplification process. Okay, there are some catalysts that can be used in this photoresist, so which can improve the chemical amplification, which can increase this chemical amplification process. Okay, so now next one is this chemical amplification process. So, and the photosensitive resin undergoes a chemical change when, okay, so as we have seen in the previous slides, so there was a novelic resist which is with a sensitizer. In sensitizer, when a photon is falling on the chain, so it makes some chemical changes. Okay, the standard one photon alters the solubility of one group of the molecular chain. Okay, but during the chemical amplification, one photon alters many chemical reactions, so it reduces the energy. Okay, it reduces the not the energy, it we require a less power. Okay, we require a less power, less intense, we can say, less intensity of the light we require. Okay, or we require lesser time, because number of photons are, if we give more time, number of photons are falling on your this photoresist will be more, so we require lesser photons and we require lesser time, and that will be a lesser energy intensity. Okay, so in the kinetics perspective, so there is a thermal annealing kinetics. So baking of the photoresist, we have in during the this process, photolithography process, or during the optical lithography process, there we are baking the substrate at several times. One is the soft bake, before, after, just after the coating of the photoresist over that, we are doing the soft bake. Soft bake is just to remove the solvent. Okay, to remove the solvent, we can do this soft bake. That is much necessary, because after that it will there will be absorption of the light by the solvent as well, and there may be some chemical reactions, and which can hamper the this photolithography process. And then next one is the post-exposure bake. Post-exposure bake is done after the exposure of the after exposing with the UV light, or with the light that is the material is sensitive to. Okay, so after that this increases the kinetics of the reaction. This makes the reaction faster. Okay, so we need to the post exposure, and that also depends on the with the photoresist to photoresist. This step sometimes this is photoresist dependent step. And then hard bake. After the photolithography, that you have done the whole process, you have done the post exposure bake, and then you have developed the developer, you have done the developer, and you have checked with the microscope that your feature size is fine. Okay, after that you can do the hard bake. After this hard bake process, you cannot develop the this you cannot develop this, because after hard baking, that there is kind of a this photoresist gets hardened. Okay, so this cannot be removed from the with the developer. Okay, for that hard bake we do. And hard bake is done for post processing. So if you want to keep it in some acid, because you have transferred this pattern over this. Okay, this is the pattern, this is the photoresist, and this is exposed, and there is something underneath that you want to transfer the pattern. If you want to do it with the if SiO2 is there, you want to dip in the HF. Okay, so you need to do the hard bake. So this will harden the harden the photoresist, and it won't dissolve in acid, that HF or HCl also, it doesn't dissolve, so you can use the HCl, and this photoresist will be intact, but it will protect this layer. Okay, so underneath, so you can transfer the pattern with this. Let me the charger. Okay, now so now this baking temperatures, this soft bake is done generally 1 minute at around 100 degrees Celsius. Okay, at around 100 degrees Celsius. And this post exposure bake is also around for 1 minute at 100 or 110 degrees. Okay, sometimes if post exposure bake step is required for image reversal kind of photoresist, there are some photoresist. If you can use this photoresist as a positive tone photoresist and a negative tone photoresist, so that works dually. So with the steps how you are doing this post exposure and post exposure bake, so that depends on that. So that also takes 1 minute of the annealing post exposure bake, and you can do. And this hard bake generally done either 2 to 3 minutes. Okay, this takes around, if you do this hard bake at this point, that won't transfer the pattern, so you need to take care of that time. Okay, if you go for the higher time, so your pattern won't get transferred. Okay. Now baking conditions or annealing conditions, there are two type of photoresist, type 1 and type 2. In photoresist with the low density is the type 1. Low density means the density is low, the chains are far apart from each other. Okay, so there is a very high large free volume is more in this kind of photoresists after the after the spin coating. Okay, and then there are type 2 which are very high density, and the small free volume is small, and acid diffusion is high in this one because of the free volume, and low acid diffusion because of the high volume, because of the small free volume. And the acid diffusion, where it is coming from, acid after the exposure of the light, that photoresist or sensitizer is converting from whatever position it is to the acidic. Okay, so that is when we bake it, that diffuses. Okay, during the post exposure bake or the pre exposure bake, or that actually diffuses. So how can you control that? With the temperature. Okay, with these, how can you control that diffusion actually? So type 1 photoresist, the pre-exposure bake should be less than the glass transition temperature. If you do it higher than the glass transition temperature, that will get hardened. Okay, that will get hardened, and may get hardened, that I'm not sure of, because of the low density. Okay, the large free volume in the glass transition, that this your photoresist turns a glassy. Okay, that can compact when you bring the temperature down. Okay, and this pre-exposure bake temperature should be greater than or equal to the transition temperature, because the already this is a very small volume is there to remove the temperature. That should turn the glassy so that the solvent can get evaporated easily, the pre-exposure bake. Okay, otherwise this is the thing. So in baking implications, so the sensitizer may get decomposed. That depends on the temperature. Okay, if you go for the higher temperature, the sensitizer may get decomposed. So during the soft baking, you need to take care of the temperature, because this sensitizer won't work during the exposure step. Then the atmosphere here, there is H2O, O2, they may affect this sensitizer if you exposed in the outer environment. Okay, and diffusion of the solvent, diffusion and evaporation. So this solvent gets diffused. Okay, so this also depends on the how you are baking your substrate. Okay, if there is a hot plate and you kept your substrate over that, and there is a film, so it is heating from the bottom, so it will start hardening, or from the bottom. Okay, start hardening from the bottom, that it will remove the solvent from the upside. Okay, so this is kind of a good thing that you need to annihilate on a hot plate. And the another thing is if you in a vacuum, in a oven, if you that annealing happens from the top. Okay, from the top annealing happens. So initially this part will get hardened, and it is very difficult for this trapped solvent to get out. Okay, so what will happen is, so these photo there you may find some cracks, a small in nanometer scale, you may find some cracks through this in the film after the baking. So these may affect the lithography process. Okay, and then there is a post exposure annealing. Okay, so after this post exposure annealing is done to chemically amplify the photoresist. Okay, to chemically amplify the photoresist, or to make the reaction faster. Okay, so if what happens at a lower temperature, the reaction, okay, this is the photoresist, there may be the exposed area. After the annealing, this part is not fully at lower temperature, this part is not fully removed. Okay, so because the reaction didn't complete perfectly. Okay, at higher temperatures you have increased the reaction kinetics. Okay, so with that you can improve your feature size. As you can see, this exposure dose, which is given 33 millijoule or 34 millijoule per centimeter square. So with with 5 degrees, this is the you can say the feature size you were getting with the mask, and this is the feature size after when you annealed at 110 degrees. Okay, so you have also improved the feature size, and you have improved the reaction. By improving the reaction kinetics, you have improved the feature size. Now this is the contrast of the resist. What is the contrast of the resist? This is the resist contrast curve. This is the contrast curve. So what is the remaining thickness with the energy of the of the of the lamp? Okay, with the energy of the lamp that you are giving, that you are providing, that is energy of the dose you are providing, with the and dose you are providing. Okay, so up to a certain how you can do this thing is, you have a substrate, you have a over that you have coated the this photoresist, and directly you are allowing this light to fall with some energy. Okay, this energy okay, you can control the energy, this millijoule per centimeter square, that you can control this from the instrument, that you want to give 10 millijoule per centimeter square or 20, 30, 40, 50, 60, that you can control. Thus you need to feed the power. Okay, that will this instrument will stop automatically after the 10 millijoule of the energy. Okay, that instrument will automatically stop. And with that, how much your photoresist is removing. Okay, if you are giving a less energy, your photoresist is not removing at all with the developer. If you are increasing the energy, as you are increasing the energy, your whole photoresist will be increased. This is the critical. Okay, okay, this is the E1 E naught, and so after this your photoresist starts dissolving. Okay, this is this gamma contrast factor. Okay, what to call it, I forgot this. So this gamma, this contrast resist contrast can be calculated with this formula, log of 1 by log of E naught by E1. Okay, this with the slope. First you need to see the slope of this one, where it cuts the x-axis. So this is the E naught, and where it cuts this, the maximum of this E1, the total thickness. Okay, so wherever it cuts, this is the E1. Okay, this energy is the E1 energy. So from this you can calculate this contrast. Okay, resist contrast. So now comes on the development. So so after the post exposure wake, you need if the positive part, if there is a positive tone photoresist, that exposed part will be removed. Okay, with a base developer. So then that can be KOH kind of, NaOH, these kind of developers can be there. Okay, development is done in a spin stage also. Okay, there are two kind of development steps that can be done. If just submerging this wafer after the post exposure wake in the solution, okay, in the developer solution, and then just removing it and keeping it. And another thing is, what you can do is, you can spin coat with that one. You just pour the developer and you can just spin coat, that will remove that. Okay, and for small samples, deep development is sufficient. Dipping in the development is sufficient. Okay, so this is the a simulated resist profile. So you have this you wanted to transfer this pattern, and how with the time how this profile is changing with the development time. Okay, initially it was here, then if you increase the development time, that you will get a very sharp kind of this feature. Okay, now there are two classes of the developer. One is the metal ion containing, another is a metal ion free kind of developers. These are less expensive, these are highly expensive, which are used for the CMOS technologies like tetramethyl aluminum hydroxide. Okay, this is kind of expensive and a bit of kind of harmful also. And because these are and CMOS technology uses this because sodium and these metal ion contaminants diffuses very fast inside a what we can say in a wafer, in a silicon wafer, and which can which are contaminants for the device, and they can hamper the properties with the device properties. Okay, but these can be used for the MEMS purpose for electromechanical systems. Okay, so like for gyroscope kind of things, for accelerometer if you want to make. So for these kind of developers can be used. Okay, now the delay factor is the thing. If you between the two processes, how much you are delaying. If you are delaying in between the two processes, that your final product, you may or may not get the final product perfectly. Okay, you're in between any process, if it is coming in contact with the outer environment for a longer time, that may hamper the lithography process. Okay, so this whole process around takes 1 hour. If you are continuously doing that thing, more than 1.5 hour, let us say 1.5 hour, but you should not give any time for the resist to expose in the outer environment, so that there should not be any effect of the humidity. After the development, you should take care in the during the development time. If it goes beyond the it gets the overdeveloped, you need to do the whole lithography process again, and that is time consuming as well as the resource consuming. Okay, now okay, okay, now let us go on the, what this delay factor can how this factor can hamper your lithography process. If there is kind of a T-top after the development, you can get this kind of profile, resist profile. This you can get a footing on the, there is a like extra this resist. So when you doing you wanted a this kind of you wanted this much of feature size, but you are getting a extra this much extra. So so this will hamper the feature size. Okay, you can get a wedge kind of no, of a resist profile, which is not required desired. So because if there is a this wedge kind of, and you are depositing a metal over this one, so this after for the lift off process, this won't get dissolved in the developer or in the acetone. So for the lift off process, it will be very hard. Okay, and how can you solve this problem is you can integrate the whole system, like you can link this lithography tool with some this whole from process can do in a single tool itself, like coating, baking, developing, and all can be done in a single system. Okay, you can optimize the process flow for that. So how much time you need to give, and how much time is for cool down time, like 1 minute, 2 minute, how much time is there. So you should not go beyond that time. So if it is more exposed to the outer environment, so that is a like hamper for your device. And controlled environment, like inside a clean room, so there is a controlled environment. If humidity is high, that higher humidity affects a lot for the development process. Okay, now and another thing, you need to design the resist the sensitivity of the resist with the UV light or with the optical light. And viscosity is if you are depositing a thin film, so how that this viscosity is affecting. So if higher the viscosity, more will thicker will be the film during the during this during the spin coating. Lesser will be the viscosity, thinner will be the film. Okay, so there will be the thickness will be more, and it will consume more energy from the for lithography during the exposure. Okay, and so if very thin is the film, so this thin film will also get dissolved during the development process. So it should not be too thin and it should not be too thick. Okay, if viscosity is very high, then you can dissolve in some in the proper solvent, and you can reduce the concentration and you can reduce the viscosity. Okay. And adhesion is critical, because if there is a problem of the adhesion, so what will happen is your photoresist will peel off. Okay, your photoresist will peel off during the development time or during any time, and it you won't get any feature size. Okay, so what you can do is you can use the adhesion promoters. Adhesion promoters. Okay, for to improve the adhesion of the resist with the substrate. And this problem, because you are using this this with the various type of substrates, let us say silicon dioxide, or glass, and gallium nitride, GaN substrate. So these kind of substrates you use for the lithography process. So the adhesion of this material of this resist should be good with this type of substrates. Okay, and the contrast, so that we have seen the contrast should be good. Okay, so this okay, if okay something is there, this contrast curve, let us go in the contrast curve. So this contrast curve should be as sharp as possible, should be kind of like this. Okay, but this is the ideal one, but the slope should be as high as possible. Okay, this slope should be as high as possible. So you need to design this your resist such that this contrast curve should be good. Okay. Resolution comes when you are doing the after the photolithography, then there is the resolution between the how small feature size you can get. Okay, that should also be there. And thermal stability, you are also going at the higher temperature, so it should be stable at that temperature, so it should not decompose. Okay, it should not decompose before the exposure to the light. And edge resistant in the sense, after the post exposure and post development, you have transferred your pattern on this resist. So after that you want to do the some SiO2 etching, let us say the SiO2 etching in HF. It should be resist to the HF after post exposure, because you want to remove SiO2 over here. This is your photoresist, so the HF will go this one and also attack this one as well, because you are just dipping it in the solution of HF. Okay, so this should be HF resistant, so this area can be protected, this area and this area can be protected, and SiO2 can be removed from this particular area. Okay, and sometimes it should be maybe HCl or some other solvents. It should be H resistant. Purity, it should not contaminate your wafer. Okay, it should not contaminate your wafer, because if there are any metal contaminants in that one, and you are using for the CMOS purpose, and that can these metal ions or these metal contaminants can diffuse down inside the silicon, and then this can hamper your device. Okay. And charging mainly comes in the in iron or iron lithography, iron milling, or some lithography is there, and another one is the electron lithography, because they are the charged particles. Okay, they are the charged particles. Electrons are charged particles, so they go when they etch, when the electron beam is made to fall on the on this on this your photoresist, so that should not get charged, that should discharge this through the underneath layer or something should be there, so that should not get charged. Okay. And substrate compatibility, because of you are using a lot of different kind of substrates, so that should be compatible with the substrate. And process compatibility is in the sense, you are after this lithography process, you are using either you are using the wet etching, dry etching, or metallization, and maybe some other process. If you are using, that should be process compatible with that. Okay. Because after the metallization, after deposition of the metal, you want to remove that photoresist with either acetone or any kind of dissolver. Okay, so that should get dissolved in that particular solution. Okay, maybe whatever is this acetone, maybe that solvent, that particular solvent, that should get dissolved after metallization, or after even dry etching or this thing, because your work is done. Now you want to remove that photoresist from, that is the kind of a sacrificial layer that you want to remove, that should get removed after that, otherwise it will hamper the device. Okay, so I think that is all for the today. So next time we will meet the next time, and next time we will do some maybe I think projection lithography we will see. Okay, so in that one there is much more of the optics. Okay, we will see. And if you have any doubts, you can write to me, or you can ask me in the next tutorial, or if you have still you have doubts, you can ask me now. Okay, so see you in the next lecture. Thank you for joining.